So what we're going to go through now is essentially Physics 11 for rotation. Now, with Physics 11, we did linear motion, and the first thing that we did was kinematics, and we defined the variables. We said x is where the object is located, and v is how fast it's going, and a is the rate of change of that velocity. Well, for the angular variables, we're going to use different variables. So for position, it's going to be the angle theta, where the object is located in radians. Just like position was in meters, theta will be in rads. Angular velocity is going to have units of rads per second. That's, of course, our familiar quantity omega that we saw back when we studied waves, and also when we looked at harmonic motion. Then the units of acceleration are going to be radians per second squared, and that's a symbol alpha, a Greek letter alpha. That's angular acceleration. So let's quickly go through rotational kinematics. And in Physics 11, the first thing we start with is velocity and understanding what it means. Understanding it as a ratio. So if you had meters per second, that was the meters of displacement each second. It's the same thing for rotation. So if you had 2.5 radians per second, that would mean each second the object would rotate 2.5 radians. Now, a radian turns out to be about 60 degrees. It's a bit less than 60. So 2.5 radians, well, that's about 150 degrees of rotation each second. So, if it started here, then the next second, about 150 degrees would be there. And then the next second after that, it's 300 degrees. It's almost all the way around. So that is what 2.5 radians per second would look like. Now, in Physics 11, we talked about how velocity was actually a vector, and you could be going east or west, north or south. For angular velocity, we can just use counterclockwise and clockwise as the directions. So, in Physics 11, it turns out that when you were moving at a steady speed, that velocity then was actually a ratio. It was the distance you traveled each second. Well, the same thing for rotational kinematics. Where you're going at a steady speed, the angular speed is going to be the angular displacement over time. Now, there's another way to measure how quickly something's rotating, and that's in terms of the period or the frequency, because we remember that both of those are related to the rate of vibration, or the angular velocity, omega. Now, here's a common unit for rotational speed, 550 RPM. R stands for revolutions per minute. Now, to put that in standard units, minute is 60 seconds, so now we see that's a revolution per second. Now, if we want its angular speed, that would be omega. And omega is not in revolutions per second, instead it's in rads per second. So now we need to say, well, what's the conversion between a revolution and a radian? Well, one revolution, or one full cycle, is just 2 pi radians. So this will enable us to calculate omega. Once we have omega, we know that period is, reciprocal frequency is 2 pi over omega. So that period will just be 2 pi over omega. And then we can just work out what that is once we know omega and see how long the period is. So let's just punch those numbers through. We get about 57.6 rads per second and about 0.109 seconds. Now, another way to approach this, alternatively, right, or we could say that this 550 RPMs, so 550 revolutions per minute, when we convert it to seconds, you see a revolution is really the same thing as a cycle. And 550 over 60 cycles per second, that's really a linear frequency, f. So we could identify RPMs as a unit of frequency, and then to find omega, if 1 over f is 2 pi over omega, we would cross-multiply omega up and 2 pi up, and then we would find the rate of vibration, the angular velocity, in this way. So we would need to take this and multiply by 2 pi. But if you look up here, that's exactly what we did here. Here we were just treating it as a unit conversion. Here we're identifying RPM as a unit of frequency and then multiplying by 2 pi to get omega. Mathematically, they end up equivalent, and there's just a small difference, I suppose, in the thinking that underlies those approaches. And you should be comfortable with both of those. Here's another constant velocity rotation problem. The tire is rotating at 1.5 rads per second. We're given the time. Where will it be? So presumably we're being asked for the angular displacement. Well, we know that omega, when you're traveling at a constant rotational speed, is just a distance over time. Speed is distance over time. So you can find the displacement just by multiplying the speed and time. So if it's traveling at 1.5 radians each second, after 2.5 seconds, you've gone 3.75 rads, which is a little bit more than pi, right? So if the object was here, then a little bit later, this would be 3.14 radians, so it's probably about there. So that's what you've done in 2.5 seconds of rotation. Okay, in addition to that, in Physics 11, we would do some graphical analysis of velocities. We'll skip that here, and then we'll move on right to the next unit of Physics 11, was acceleration. Now, one of the things that we worked on in Physics 11 was understanding what acceleration really is. So if you look at 3 radians per second squared, we know that a velocity was like a distance over a time, right? Rads per second. But what would a rad per second squared be? That's the radians you go each second squared? That doesn't really seem well defined. Well, you may remember that the way to interpret it in Physics 11 was to say it was rads per second per second. So to interpret the unit, you need to write it in this way. Obviously, mathematically, that's equivalent to a rad per second squared. So what does this mean? Well, it is the change in angular velocity over the time. So this means if you're starting at rest, that means your initial velocity is 0, right? And so we could represent this as a chart, right? So you're starting at rest. After 1 second, because it's plus 3 rads per second, you're then going at 3. And each second, you would be going up by 3. So that's what acceleration is. It's the ratio of a velocity change to time. So I'll write it as a word equation. Change in velocity per unit time interval. And in Physics 11, we would talk about the direction of accelerations, and we would say that, okay, if the acceleration was, say, negative, that really means that the object is being pushed in the negative direction. And so if you were to start at 5 radians per second, that's positive. So you're moving to the right, you're pushing to the left. So the speed is going to decrease. It's going to start at 5, then after 1 second, it's slowing you down. After 2 seconds, even slower. So the negative really refers to the direction of the acceleration or the direction of the push. So this would be pretty common stuff for Physics 11, and we might write it this way. In Physics 11, this is the word equation for the angular acceleration alpha. Now, when it came to doing calculations with acceleration, in Physics 11, we had to say, okay, it's no longer true that a speed is a distance over a time when you're accelerating. It's also not true that omega is distance over time anymore. So what is true? Well, so we just said that's no longer true. Right? What is true? How do you find a speed? Well, a final speed is an initial speed plus an acceleration times time. That was just like in Physics 11. Vf is vi plus at. And how do you find a displacement? Well, a displacement is not a velocity times time. Whoops, writing the wrong one. Ha ha ha. Sorry, just getting ahead of myself there. A displacement is an average velocity times time. And when you're accelerating constantly, your average velocity is just the sum of the velocities over 2. Same thing here for an angular displacement. It's the average angular velocity times time. So the other two Physics 11 equations are very easily transmuted into rotational equations. Displacement is an initial speed times time plus half times an acceleration times elapsed time squared. A final velocity squared is an initial velocity squared plus 2 times an acceleration times a displacement. Okay, and here is a typical problem. So why don't you stop the video for a second and try this question out, and then see if you get those answers, and then we'll play the video in a second. And we're going to talk about this one in a little bit more detail when we meet in class. So pause the video, do this problem, and then compare with my solution. Okay, so here's my solution. You can skip ahead if you've already got it. So we have an initial speed, omega initial of 120, and if we're slowing down, that means the acceleration is going to be in the opposite direction, so we need to introduce a minus sign. If we want to find the time to stop, when it stops, that means the final angular velocity is 0. So final speed is initial speed plus acceleration times time. 0 is 120 plus minus 4t. T is 30 seconds, putting in the correct units at the end. How far did it go? Well, an angular displacement is an average velocity times time. It's starting off at 120 rads per second and slowing to rest over a 30-second time period. So this is 60 times 30. That's 1,800 rads. Note, how many revolutions is that? Well, there's 2 pi radians in a revolution, and 2 pi is about 6, so you can see we have about 300 revolutions here to stop this. It takes quite a few rotations for it to come to rest. So that's some basic angular kinematics. There's more to it than that, though, because rotating objects, yes, it's true, there's an angular displacement. They travel a certain angular distance. However, there is also a linear distance there. So let me fix that up. Okay, we seem to be working again. So for that angular displacement theta, you'll see that a point on that object travels a certain distance. Now that distance is an arc length s. And you may recall from previous mathematics courses that the angle is a ratio of the whole circle angle. Is the arc length divided by the whole circle distance, which is circumference. Sorry, I ran out of room there. And the circumference is 2 pi r. Rearranging, we get another way you might have seen this is actually the definition of an angle in radians. It's the arc length over the radius. All right, so what we see there is the linear distance is r times the angular distance. And, oh, sorry, I should say that because of that, as the distance increases from the center of rotation, you travel a greater distance, right? This is clearly further than this blue line is. And that just says if you rotate your arms in a circle, your hands travel a lot further than your elbow does, and your shoulder or your upper arm hardly travels any distance at all. Now, for linear speed, that's going to be the distance over time. Sorry. And the distance, well, that's the arc. And so this is r, based on what we just wrote down, times the angular displacement theta over time. But this, of course, if you're going at a constant speed, is omega. So what we've got then is that the speed of a point on the rim depends on how far you are from the center of rotation and on the angular velocity omega. So just as your hands are actually going further than your shoulders, they're also moving faster than your shoulders. And that's why in sports we always talk about making full extension, say with a racket when we're about to hit a tennis ball. So here's a practice problem, and this is a good visualization. This is a compact disc, which people used to use to listen to music. And as that rotates, the point at the center, which is at r equals 0, will actually be at rest. Then this point, which is halfway out to the edge, will have half the speed that this point on the edge does because it's further from the center of rotation. You may have noticed if you watch bicycle wheels spin that the spokes are blurry out here, but then in here you can make them out. They're a little bit more distinct. That has to do with this relationship here. So point A, with no distance, there's no speed. Point B, oh, this says on the rim, so we're way out here on the rim. So it's 4 centimeters of radius times 65 rads per second. Let's see, that's 240 plus 20 is 260, so this should be 0.26 meters per second. And then I'm just going to drag this, give myself a little bit more room here. If it'll let me. There we are. Screw it up. Nope, didn't like that. Okay, so I'll just do problem C over here. You'll have to just squeeze it in there. Now, with half the radius, you end up with half the speed, about 13 centimeters per second for this point here, halfway out. This example 6 relates to a demonstration. We'll do that one in class. Now, we're not yet done because we've related linear acceleration. Whoops. Seem to be having issues here. Just let me pause and fix this quickly. Okay, yeah, hopefully that's working again. So, yeah, one interesting geophysical application of this is the Earth. If you look at the Earth on its side, it's the distance from the rotational axis that matters. So right up here in the pole, there's no distance from the rotational axis and therefore no speed. At the equator, you're a distance r from the rotational axis, where r is 6,380 kilometers, the radius of the Earth. Notice that at Vancouver, because of the latitude, which is about 49 degrees, you're actually a little bit closer to that rotational axis. If that angle's theta, then this angle's theta, so it's r cos theta, where theta is the latitude angle. So at Vancouver, here at the equator, it's r omega, but here at Vancouver, it's about cos 49 times omega. And that actually has some influences weather systems and creates an effect where storm fronts, say, rotate around low-pressure centers in a clockwise direction in the northern hemisphere. Now, what is omega from the Earth? Well, here's a trick. A way to find omega of the Earth is to remember that it's 2 pi over the period. And the period for the Earth's rotation is 1 day, which is 86,400 seconds. So you kind of have to remember that trick. If you work it out as a decimal, it's 7.27 times 10 to the minus 5 rads per second for the omega of the Earth. But do remember this trick, because we will use it pretty often. So thus far, we've seen that arc length is r delta theta, and we've seen that v is r omega. What about the equivalent relationship for acceleration? Well, true to pattern, a will be r alpha, where alpha is the angular acceleration. Excuse me. Sorry about that. So there's alpha. And then this is the acceleration of a point on the edge. And I'm calling that a in the theta direction. The reason I need to add that little subscript is that there's actually another acceleration. There's the inwards acceleration, v squared over r, corresponding to the changing direction that we're familiar with. So a theta happens when the object is changing in speed. Ar, the radial acceleration, happens when the object is changing direction. Now this one's inwards, and this one's along the edge of the circle, consistent with the direction of alpha. So here's a simple example. So here we've got a bird, and it's flapping its wings. So this is the bird's body, and these are the 2 wings. So as the wings swoop down in this direction, there'll be an inwards acceleration, and there'll be an acceleration in the theta direction. So these birds start off at rest, so the initial angular speed is 0. They speed up to 4 rads per second in 3 seconds. Sorry, just another coughing fit there. So we'll use the acceleration equation to find the angular acceleration. It's 4 over 3, or 1.3 rads per second squared. So that means this one, which is r alpha, the end of the wingtip is, because they're 50 centimeters long, it's 50 centimeters from the axis of rotation. So multiplying that by 1.3 repeating, we get 0.6 meters per second squared of acceleration along the edge of the swing. There will also be an inwards acceleration, and that is going to be v squared over r. That means we're going to need to know the speed of the wingtips. The speed of the wingtips is changing here, but it asks us for at the end of the swing. So for the final velocity, we can do r times the final omega, which is 4 rads per second. And we can say that at that point the wingtip is going at 2 meters per second. So the inwards acceleration v squared over r is 2 squared over 0.5. That's 4 over 0.5. That's 8 meters per second squared. Excuse me again. And so there's an inwards acceleration of 8, and there's an acceleration along the edge of the circle, along the tangent direction, of about 0.6 meters per second squared. So to recap then, for rotational kinematics, first of all, for constant speed, speed is distance over time. For acceleration, we have the familiar equations from that correspond to a Physics 11 constant acceleration equations. Then we're adding in these three results here to relate the distance and speed and acceleration of a point on the edge of the object to theta, omega, and alpha. A reminder, of course, that there's actually two accelerations for the point on the edge of the circle. And of course, all of the other Physics 11, once you've got v, you could do Vf is Vi plus At, etc. So we'll be using those equations as well. So this is an introduction to rotational kinematics. And we'll talk more about this in class.